All right, class, welcome to video 7.1. Today we'll be talking about the marginal rate of substitution. I'll do some examples and I'll show you some special indifference curves from this. I'm excited. So before we get started, you should have read pages 66 to 73 in the textbook. And this is how individuals trade off between two goods and or activities. And it's going to be crucial to solving the type of problems that we're interested in solving, like how do individuals get the optimal bundle. So this is really important. And so basically the main question we're going to be asking today is how much of a good 2 do I have to gain to give up some of good 1 and remain equally happy? So it's kind of like if I give up some of good 2 and substitute some of good 1 for it, how much extra good 1 do I need to remain equally happy given that I've given up some of good 2? And, except for very special cases of indifference curves, there's usually nonlinearity. So how much you have to give up will depend on the initial value. So I'll show you a picture of that right now. So let's just imagine we're walking into Morgantown Target. On the right is a Starbucks with pumpkin spice lattes, and on the left are sweaters. Given an indifference curve, we have the same utility from consuming different combinations of lattes and sweaters. So here's our indifference curve here in latte sweater space. And we're just going to characterize how individuals substitutes across these two options, given that, where they start on their indifference curve. So, like I said, how much good 1 do you have to give up to make up for losing good 2? Good 2 being sweaters to be equally happy. And so we see that if you were consuming a relatively large amount of lattes and a relatively few amount of sweaters, then if you want to give up some latte, then you don't really need that many sweaters to give up just some latte, and that's because you already have a lot of latte. So sweaters will be valuable compared to the amount of latte that you already have at that point. And so we're just interested in this slope, and this slope defines how much you're willing to give up to stay on that indifference curve. So you're willing to accept relatively few sweaters to give up a small amount of latte if you have this much latte and this many sweaters. Now, you're willing to, this slope is about -1, so you're willing to accept about 1 sweater for 1 pint of latte or ounce of latte here, right at this point. And if you're at the end, then you need a lot of sweaters to give up a small amount of latte. And that's because you already have so many sweaters that giving up some latte, you'll have to be compensated quite well because you have very little latte. And it's kind of consistent with diminishing marginal utility here. So notice that these changes, this marginal rate of substitution, the slope is different at different points on this indifference curve. So the slope is a function, or the marginal rate of substitution is a function of where you are on the indifference curve. And so I want to take a second to formally define this for you and do an example. So you know your utility is a function of good 1 and good 2. And importantly, you need to have the marginal utility is the additional utility from consuming 1 more unit. So the marginal utility from 1 more unit of good 1 is a change in utility given a change in good 1 equals the marginal utility of good 1. And so to get the slope of the indifference curve, the marginal rate of substitution, which we've been talking about, you need the change in good 1 and good 2 that leave your utility unchanged, that keeps you on the same difference curve, because we know that on the same difference curve, you have the same level of utility, this U bar here. And so to simplify our lives mathematically, we're going to redefine Q2 as a function of Q1, aka as a kind of an implicit function here. And that's because you can define where you are on Q1 or how much Q2 you have as a function basically of how much Q1 you have for this given indifference curve where your utility is constant at all bundles on it. And so basically on the same indifference curve, Q2 can be calculated from Q1, which lets us do this. And so then we need to answer the question, how much does Q2 have to change by if we increase Q1, which is this little function here, given that we require utility to remain constant, it's this U bar. And so to answer this question, we take the derivative of the indifference curve, which is defined as u as a function of q1 and q2 as a function of q1 with respect to q1. And so this is kind of what this looks like. A change in utility given a change in good 1 is just the marginal utility with respect to good 1, and then the marginal utility with respect to good 2. And because q2 is only changing because q1 is changing, as we have this implicit function here, we need to multiply by the change in q2 that happens due to a change in q1. And so that's where this dq2 dq1 term comes from. And so then the rest of this is just going to be me simplifying this kind of expression for you. So we notice that we can write this expression basically as u1 plus u2. This is u1, this is u2, times this. And then something else we need to notice to get to the next point is we know that the change in u given a change in q1 is constant because we're staying on the same indifference curve. So by definition, this change in a constant is 0. So 0 because utility is constant on the same indifference curve. And so we get 0 equals u1 plus u2 times dq2 over dq1. And we can rearrange these terms to get our definition for the marginal rate of substitution, which is negative u1 over marginal utility with respect to good 1 over the marginal utility with respect to good 2. And so we know that the slope of the indifference curve is the negative of the ratio of marginal utilities. And this is going to be extremely important for you to keep in mind as we keep going forward. And so I wanted to solve something that the book has solved for you because this is probably not straightforward and involves calculus, which is not a prereq for this course, but will be necessary. So suppose Jackie has what economists call a Cobb-Douglas utility function. This is utility equals good 1 to the a power times good 2 to the 1 minus a power, where a is greater than 0 and is a positive constant. So let's consider q1 tracks of recorded music and q2 number of live music events. We want to know what is the marginal rate of substitution for this utility function here. And so we know that the marginal rate of substitution from the last slide is just the negative of the ratio of marginal utilities. And so what we're going to need to do is we're going to need to differentiate this function with respect to good 1 and with respect to good 2. And so I'm going to start with the marginal utility with respect to good 1. And so we need the product rule here. So this is derivative of two terms. F and g is f prime g plus f g prime. So we need to take the derivative of this with respect to good 1, multiply it by this, and then take the derivative of this with respect to good 1, which is 0. So this will drop. This term will drop out. And we're considering q2 like a constant. So for those of you who had head calc 1 and a couple video, or I think last video actually, I linked to a couple open source textbooks that will help you with the product rule and exponent rule, as well as the Khan Academy videos that I shared in an earlier video. So you should be able to figure those out, and I'm doing my best to help you here. So utility of 1, when I take the derivative of utility with respect to good 1, I get a q1 a minus 1 times q2 1 minus a. And then I need to take the derivative with respect to good 2. Again, need the product rule, considering q1 constant. And this is the derivative of the utility function with respect to good 2. So if I change good 2 by a little bit. And you can kind of see here that I wrote it out here, and then the 0 goes away, obviously, and rearrange some terms. You should check to make sure that you know that this negative a is positive a when it's in the denominator instead of the numerator, or vice versa. So you should make sure you know how to simplify that. And then to get our marginal rate of substitution, we can just plug u1 into here, u2 into here, and there should be a negative sign here for this negative ratio. But I put the a and 1 minus a outside. You can, and the book actually does solve this and simplifies this a little bit more to make it easier to look at. But I didn't need to do that here. I just asked this, and so this would be a valid answer for the marginal rate of substitution. And so yeah, that's all problem 3.2. And now I'm just going to talk about a couple of special cases of indifference curves that you should know about that might help you with some of the intuitions. So Let's start with perfect substitutes. Trade off the same amount regardless of how much of either one has. And so the indifference curve is just a straight line. And it does not matter how much you initially have, you're always willing to trade the exact same amount. And so we know the indifference curves don't cross. And so you can draw in some other indifference curves where obviously you're the most happy to be on the highest, least happy to be in the middle, and least happy to be in the smallest indifference curve. And so some examples of perfect substitutes for me is Coke and Pepsi, because I really don't taste a difference between them. Sorry for all you people who have a hard choice, but I don't think they're that different. And then another one might be like cash and credit cards. So if you have $1 in cash or $1 in credit card, it'll still buy you the same amount. Just kind of abstracting away from like cash fees or credit card fees, or whatever. So these can be kind of also perfect substitutes. Perfect complements, you will not consume one without the other. I think these are kind of interesting. Slope is a right angle point from equal amount of each. It does not matter how much you have of one, you're always willing. You need to consume these in the exact same proportion. And so since they don't cross, you can have these other indifference curves of perfect complements. And some examples would be like a right and a left shoe. So if good 1 is a right shoe and good 2 is left shoe, you can give me, hundreds of right shoes, but if I only have one left shoe, then this is going to be my indifference curve. And you can see the same way if I only have a ton of left shoes and then only one right shoe, and it's the same. And some other examples I could think of off the top of my head would be like a video game disc and a video game console. So you have one PS2 game, you need one PS2 to play it. And same thing, kind of like I'm using a wireless mouse here, and I can only use this one wireless mouse with one other wireless receiver. And so I need to consume them in the exact same ratio. And then imperfect substitutes, this is the one we see the most. The amount you have to give up to get the other to stay on the same utility, or say the same satisfaction or same happiness, depends on the initial amount you have, and is consistent with diminishing marginal utility that I kind of talked about earlier. The shape is convex, and it matters how much you initially have. Since they don't cross, you can plot out all the other indifference curves here. And food and clothing are examples of imperfect substitutes, along with most other things are kind of imperfect substitutes for one another in this class, and just other places too. And the last thing you should know about are these quasi-linear indifference curves. It's just, if you pick the same Q at any indifference curve, the slope is going to be exactly the same. And it just simplifies comparisons across indifference curves. An example of this would be like utility of square root of Q1 plus Q2. And at any Q, the slope is the same across all the same indifference curves. And so the conclusion of this are the marginal rate of substitution is the slope of a point on the indifference curves. It characterizes how an individual is willing to trade between the two goods. In the next class, we'll go beyond willing and incorporate the ability to pay also when we talk about prices and income and how that fits on an indifference curve analysis for solving optimal bundles. So anyway, thanks for tuning in. Keep working hard, and I will see you on Thursday.